This is Dr.Senthil, Associate Professor, Department of SNS College of Technology. Now the subject is Digital Electronics and Linear Integrated Circuits offered to second year EEE students. Our student whose name is Kavipriya, Lakshika, Satya and Varsha is handling case study topic for a dice simulator, a digital dice simulator. They are going to discuss about a case study on digital dice simulator which comes under sequential logic circuit. You mean they are going to design about counter circuit which counts a digital dice simulator. Now let me discuss that case study.
My name is Kavipriya. I am from EEE Department second year. Today I am going to explain state table or excitation table. Before going to this topic, I am just going to recall about a digital dice simulator. So it is a counter circuit which generates 1 to 6 numbers. So according to the die number, we are taking two state table. So present state, next state and the output. So present state contains QA, and next state contains QA plus 1, QB plus 1, QC plus 1. So these are the binary values for 3 liquids. So just we are given enable number because the die contains 1 to 6 number and that's the repeat the number going to repeat. So by this truth table we are going to solve this. This Q is QA and QN plus 1 is QA plus 1. So this is called present state and this one is next state and this one is output TA, TB, TC. So for Q, first they given 0 and for QA plus B they are given here QN 0. So 0 into 0 we are going to take 0, TA value 0 and the next value is 0, 1, the output is 1 and 0, 0, the output is so they are given QB value. For QB value 0, QB plus value, B plus 1 value 1. So 0 into 1, the output is 1. And for QC, the value is 1 and C plus 1 the value is 0. So 1 into 0, the output is 1.
And similarly, we can able to solve with the help of two tables. We can fill this table completely and such that this excitation table is fulfilled. After this excitation table, we have to minimize with the help of K-map and we have to derive the expression for drawing the logic circuit. As the next step is carried by another method.
As I have told that to substitute all these values, so 0, 1, 2, we have substituted and for there is no zeros and 15, so we have to substitute D for that. It is not. Don't care. So we have to substitute D. D is don't care. We don't want to take that. And now we have to take a pair. There is no quad, so we have to take a pair. This is one pair, and this is one pair. This is one pair.
Another time. Take mine.
We have derived two equations which is TA and TB from the K maps. So here we can see there is E bar QC plus E cube complement. So we can rewrite this as E complement of Q bar C. So next we can move to the logic gates. So this is our logic diagram. Since we are using T flip-flop, we have chosen TA, TB and TC, three flip-flops, namely A, B and C. So the first equation we've got is TA equal to E bar QA QC E bar QA QB plus E bar QA complement QC complement. So we are introducing a term E and a NOT gate because we are having E bar here. So and the first input goes to TA. So we are having 1, 2, 3 AND gates. So we're drawing 1, 2, 3 AND gates. So in the first connections are from E bar, QB and QC. So I'm going to take a connection from E. I'm introducing a NOT gate here for the E bar and I'm going to connect it in 2 AND gates. You can see the connections here, this way, here. So I have connected it to 2 AND gates. And then next, QB, QC. So I have my QB here and QC. So I have taken a connection from QC and connected it here in the AND gate. And another one, we have 2 QB in 2 AND gates. And one more connection from the same QB, and I have connected it in the first AND gate. And the next, QC. So this is my QC. So from here I have taken a connection and connected it here. So likewise I have connected all these AND gates, and at the end of this I have connected a OR gate to get the resultant answer. And the output and the input goes to TA.
Okay, as per this expression, it means 3 AND gates comes into the picture, and the output of 3 AND gate is connected to an OR, whereas the output of OR is connected to TA. This is your TA. This is the input of A flip flop, TA flip flop. I think that TA is your most significant bit, and this is your least significant bit. Right? The output is taken from TA. You mean QA is the first output, and QB is the second output, and QC may be the third output. Right?
So the applications of this dice simulator using Mod 6 counters are, we can use it for digital dice games such as board games such as Ludo, Monopoly, and also for business such games. And we can also use this for probability experiments in classrooms. And this, especially this simulator, is very cost effective and also reliable.
Thank you for presenting this case study. Thank you, students, and thank you for listening.